used to using a microphone, so pardon me if I stumble. Thank you so much for coming here this evening. That is a fairly momentous lecture for us, and I hope it's momentous for all the right reasons, because those of you who know Mr. George will know that he has a bit of a reputation. Now, bangs, pops and all the rest of it are definitely Mr. George territory. And over the years, I think he has made his name, I think it would be fair to say, in specialising in this area. That said, I would be lying to you if I was not a little worried tonight. Setting fire alarms off is Mr. George's absolute expertise. I think I'd been in the school maybe 5 minutes. The alarm had gone off and everyone else knew. You know, I was new to the school 6 years ago. Everyone else knew, oh, that'll be Mr. George, obviously. Just routine.
I wasn't even in the school.
But we're still blamed. So I am, as I say, just ever so slightly worried tonight. Very much hoping that the Discovery Centre and the Livingston Lab is still standing by the end of this, so it might just test it to its absolute limits. But it is a really special night for us, joking aside, because as you all know, Chris has made a wonderful contribution to this school over many, many years. Actually, it is 17, Chris, is that right? Yeah. So 17 years of fantastic support for this school, and the amazing place that science has within this school. I don't think it would be an exaggeration to say lies a lot at Chris's door. As you know, he came first as a head of department, but then developed in 2007 the specialism here at school for science specialism. And now I think we have that reputation in the area, certainly, as having a wonderful facility for science. Not just this Discovery Centre, I'll come on to that in a moment, but actually because of the teaching and the energy and the inspiration that our young people gain. And I have to say, in my 6 years, I've seen that in bucket loads from Chris, and it's something very special that we have here at the Latin, and I'm very grateful for Chris for that. I won't put him off his stride excessively, so I maybe better not go on too long. But it is something special, and that was brought to its culmination here in the Discovery Centre, and Chris was central to establishing a vision. And this lab was really part of Chris's vision. You know, he is rooted in this community of Buckingham and trying to ensure that as many young people and many maybe people from across the generations love science as much as he does. And when we were talking about the layout of this lab, Chris was really keen that we were able to do something that brought people into the school. And look at us tonight, isn't it fantastic? You know, I think this is the dream as reality, actually. And just to finish, we had one very special meeting with the Livingston Trust, and it was at a very, very early stage, who very generously have made this lab possible. And at that meeting, we were just sitting down. We hadn't met the trustees at all. And Chris happened to wander by and came in and sort of blew everyone away with this passion for science. I know you'll see that tonight. I hope you have a really enjoyable evening, and it gives me great pleasure in introducing Chris George.
Oh, yeah, mic, sorry. Let me just switch it on. Not that I think I need it, but I think I'm being recorded, so... Is that all right, Aaron? Cool. Yeah, let me welcome you here today as well. I kind of thought there was going to be about 30 people here. I thought it would be, me having a bit of a laugh with 30 people. So having a bit of a laugh with sort of 230 people. Hopefully we'll have a little bit of fun together. That's the title of my talk. Now, I know some of you might be sitting thinking, well, actually, that's not true, Chris, because we heard something that actually it wasn't going to be that. It was going to be that second one, which is basically the same as, which is basically the same as that third one. Because I discovered technology doesn't work. I discovered very early on that basically being a chemistry teacher was the same as being able to blow things up and just get away with it. Hello, look, there we go. We'll have that slide up and we'll come to that in a minute. But I realised that actually I could blow things up and get paid for it. And it was such a cool career because no one would look and say, that's a bit dangerous. He must know what he's doing because he's wearing a lab coat and he's got some specs on. He must know what he's doing. And I've conned three head teachers at the school to effectively say, look, I know what I'm doing. So today I just want to give you a whistle-stop tour, if you like, my favouriteest experiments. And my first favourite experiment is kind of a bit of a weird experiment, okay? Because it kind of looks really, really dumb, okay? Nothing's happening in those two, but I'd like you to shake that one. And I'd like you to shake that one. Just give a really good shake. Just really good shake, really good shake. Then hold it up so people can see what's happening as you hold it up. Okay, this is a really weird experiment because it seems that this experiment is controlled by shaking. And look, this one's now changing. This one's changed colour again. I've stopped shaking. But just start shaking again. Start shaking. Shake it, shake it, shake it, shake it. And as you shake it, it goes blue. And if you stop shaking it, it starts to stop going blue. I think this is a bit weird. This is a bit weird. This one has stopped. See, we stopped shaking it. What I do, just keep shaking that all the way through. Just very often, just shake it. When it stops going blue, just shake it. So what is happening in here that I can basically shake it and make it go blue? Because that's a bit weird. But actually, it's a very simple experiment. This stuff contains a chemical called methylene blue. And I thought, because there might be some scientists in here, I heard the U3A were coming, I thought they would want some science. Okay, so this is for you. This stuff contains a chemical called methylene blue. And methylene blue is this really complicated structure. There it is. There it is. It contains 4 different elements. It contains carbon, it contains hydrogen, it contains nitrogen, and it contains sulfur. And methylene blue can be oxidized, i.e. you can add oxygen to it, or it can be reduced, i.e. you can take oxygen away from it. And when you add oxygen, because up here there's air, so when I shake it, I'm just forcing air, which contains oxygen, about 20%, into the methylene blue. The methylene blue is oxidized, and it turns blue. Now I've got another chemical in here, namely sugar, or glucose, and when glucose reacts with methylene blue, the glucose reduces the methylene blue, takes the oxygen away from the methylene blue, and methylene blue without oxygen is colourless. So this is a very simple experiment. Might look kind of bizarre, but it's very, very simple. Just keep just keep shaking it. Whenever you get bored, shake that. Then I'll know how bad I am. Because if you're shaking, I think, okay, you need to liven it up. Okay, now this experiment only works if you shake it. It will go blue, it will go colourless, it will go blue, it will go colourless, but I have to shake it. I have to do something. This next experiment, or experiments, because we want on either side, is kind of weird, if it works. Now I have to admit, you will discover, if you know anything about chemistry teachers, is chemistry teachers actually only work because behind the chemistry teacher are 2 glamorous lab technicians. Okay, we happen to have 5, I think, in this school, but one of them who's worked very closely with me over the last 7 years basically set all this up. And another one set this experiment. So this experiment works. Okay, you blame Mrs. Buchanan. Norma, that's your fault. This doesn't work. Okay, if this one doesn't work, you blame Miss Weatherly. Okay, it's very simple. So Sarah Weatherly, this is your one. Norma, this is your one. If it fails, This is down to you. I didn't touch these. I did it with bucket chemistry, and it didn't work. They've assured me this works, so we'll see. He says, hopefully. You can see, they've weighed it all out. Normally you'd weigh things out, they've weighed it all out for me, so I don't have to do anything like weighing stuff out. And we'll see, hopefully, if that will start to do something on that side. Do you say 100 of each, Sarah? Okay. 100. Height and proximity. It's changed orange, so that's good. It's done something. Keep watching it. 100 of that one, and then 100 of that one. Okay. Now we keep watching them. If it gets boring, you start shaking. Is it doing anything? Have they changed? No. The great thing about science, especially chemistry, is sometimes you're so convinced the experiment will work, and then when it doesn't, you have to start looking at them and thinking, let's just leave them running. What? Is that changing? Is that going colourless? Yes. Excellent. Keep reading this one. Okay, now this is a kind of bizarre. So it went from colourless to red. It's now gone back to colourless. And if we keep on watching, this experiment is the kind of the most weirdest experiment because it's just gone red again. No, I've not done anything to this experiment. And if we keep watching, this experiment will suddenly start going back colourless. See, science, chemistry always works ultimately. So you have to be patient. Okay? And this is what we call an oscillating reaction. Because for the next 10 minutes, this experiment will just oscillate. From dark, red, back to colourless. There we go. Red's gone. It will come back. This is now changed. There we go. It's always good to keep your eyes on everything. Back. The red has come back. Note. Okay. This will start to go in a minute. The red is coming back. And there we go. It's gone. Okay. I will say, at various points in this, you are allowed to go, woo! That's good. Okay, you are allowed that. That is allowed. There we go. The colour's coming back. Note. The colour's coming back. And there we go. Okay, so what on earth is happening in these two? Because seemingly two reactions are taking place and I'm just standing here doing absolutely nothing. And yet actually this experiment is very similar to that one there. Very similar to the very similar to that experiment there that's going blue as we shake. The difference is all of the chemicals that I need to make it go from one colour to another colour are already in this flask. Already in this flask. There we go. So, these are really famous oscillating reactions. They're from about the 1930s, 1940s. Two chemists, one called Briggs and the other one. What they realised is if you mix various chemicals together, and the ones in bold, okay, are the chemicals that are present in the flask at the beginning. And two reactions take place. So in the first reaction, effectively, you have colourless manganese ions, and you convert them to red manganese ions. But note in the second experiment, the red manganese ions are converted back to colourless manganese ions. And then these two reactions just oscillate backwards and forwards, backwards and forwards. And they will keep on doing that until either this chemical, malonic acid, runs out. And if that runs out, can you see the second reaction can't happen? It would stay red. Or the bromate ion runs out, and if the bromate ion runs out, the top equation can't happen, and it will remain colourless. But while you've got all of these bold chemicals that I put in all at the beginning, it will just oscillate. And chances are it will oscillate for the next hour, backwards and forwards. The second one, by two chemists. You can decide how you pronounce either of those chemists, Boulous and Zabotinsky. They did exactly the same thing, but over here, okay, what I'm forming effectively in that blue-black is iodine. Now there's about 6 or 7 other experiments that happen down here that form iodine. Okay, basically I could have spent the whole lecture just going through that oscillating reaction. Okay, you'd have all got very bored with the sheets and sheets and sheets of chemistry. But again, in a sense, 2 reactions are just taking place, and they just oscillate backwards and forwards. And when you produce iodine, it goes blue-black. When the iodine is destroyed, it goes back coloured. Again, it will just keep on oscillating backwards and forwards while all of the chemicals are there. And basically what we did, we added all of them in excess. We added many, many more, much, much more than we needed of all of the reactants. Because see, that's been my passion since I think I was about 4. When I was 4, I discovered, probably illegally, I discovered matches when I was 4, probably because I had an older brother, okay, and he and I discovered matches. And I discovered, don't ever do this by the way, but if you rip the heads off the matches, okay, and you pick a big pile of them, and you get a magnifying glass, and it's the summer, okay, you can do some really cool things with matches. And I started wondering, well, why does that happen? Why does that happen? So then, by the time I was 7, my parents bought me a chemistry set, and I looked at the chemistry things you could do in the chemistry set, and I thought, how dull are those? So I went into my dad's garage, and I just looked at what things he had in his garage, and I'd pull those out into my chemistry set as well, and just sort of start mixing until something either went bang, or produced some kind of smell, or preferably both of those. That would be the really excellent chemistry. Because I wanted to know why. And I thought by experimenting, by trying, by doing, I can start to think why. Because as a chemist, that's a really important question to ask. Now, the other thing I did when I was a child, and if you bought chemistry sets, you will know that almost certainly they will have some sodium hydrogen carbonate in the chemistry set, almost certainly. They might say, go and raid your mum's kitchen and get some baking powder as well. And they'll probably not have citric acid. It will probably say, go and get some vinegar from your mum's kitchen or from your dad's kitchen and mix the two together. Mix the two together and see what happens. Okay? So I thought to myself, well, that's kind of cool. That's kind of cool. So I pinched from the chemistry department some sodium hydrogen carbonate. More is good, isn't it? Yeah, more is always good. Has anyone ever added sodium bicarbonate to vinegar? So what happens? It's like a volcano. How cool is that? Okay, so here we go. We're about to have a volcano. Keep shaking. You won't. We'll do it over your head because you're a Latin. It doesn't matter. Okay, here we go. Now that was wholly unimpressive, wasn't it? It was wholly unimpressive because actually I know something about acids that you learn about probably in about year 7 when you get to school, or if you've done a year 2 science fair with us, you learned when you were in year 2. Because when you were in year 2, you would have learned that It's okay having citric acid and sodium bicarbonate, but if you want an acid to behave like an acid, you have to add water. And when you add water, okay, the reaction will take place. This is quite a cool reaction. Just hold that flask. What's happening to that flask? Is it getting hot or cold? It's getting really cold. Is that getting cold? Is that getting cold? This is a reaction. It's got an endothermic reaction. It's taking in heat from the surroundings, therefore cooling down this flask, and it will just get quite cold. So I thought to myself, well, okay, that was quite cool, but what would happen if we did exactly the same experiment? We do this for year 2. Probably one of my favourite experiments in year 2. And now I need about 4 volunteers. Okay, young man in green, you were very quick. Yeah, young man in middle in grey. Yep. Yep, young lady right at the back. Yeah, young lady at the back. That'll do. That's 3. And young lady here, that's 4. That's cool. Okay. I'll set them up for you because you don't want to too much. All you're going to do, okay, you're going to add the water. Okay, put the lid on. Now, at year 2, we do this and we fire the chemicals into that. People will get very cross by that. So when you put the lid on, what you do is put it upside down and then just stand back. Is that okay? So, right, do you want to come this side? Before we want to come this side, let's put some citric acid. So, let's think what's going to happen. We've got some sodium bicarbonate, we've got some citric acid. When we put the lid on, give it a shake, nothing happens. Note, no explosion whatsoever. But when we add some water, we're going to get that fizzing that we saw in that beaker. So when we get that fizzing is carbon dioxide. That gas is going to want to escape. With the lid on, the only way that gas is going to escape is by taking the film canister and exploding it upwards. There we go. That's your one. Just take the lid off, put the water on, and then turn it up like that, okay? I know. Don't worry, they protect your eyes. As much as you want. Put the lid on, put the lid on, put the lid on, put the lid on. Yeah, turn it upside down. Okay. Number 1. See how much mess we can make before we actually before I get told off. There we go. Oh, keep that one up. Okay, number 2. Yankees, let's just throw the lid away. I may have just thrown the lid away. They use that lid. Turn it upside down, turn it upside down, turn it upside down. That's it. Just put some water in it.
Yeah.
It's like a firework. You think, do I go and look at it? We'll come back to that one. We'll do that one again. We'll just leave that one there for now. Because if not, we'll get you to add some more water into it, okay? Because I don't think that's going to go. Unless I did, I don't know. We'll see. Just give it a bit of a shake for you, okay? There we go. Water in. Let's do the last one. That's the boy thing. They're just thinking, do you want to do it for them? We're going to do it, you should put loads of water in, just a little bit of water in. Oh, actually, I think you need more water. Put a bit more water in, okay? Put a bit more water in. We'll put more water into these two for you, okay? Give it a bit of a shake. We'll open this up. Yeah, we're going to put a bit more water into that one for you, okay? You do that one. Push a load more water into that one, okay? In a minute, there we go. That's it, now put the lid, that's it, now put the, get that lid on, get that lid on, get that lid on, get that lid on. Get that lid on, close it up tight, turn it up tight, close it up tight, that's it, turn it upside down. Let's see if we can get it, let's see if we can get that lid on again. So we get a second one. We'll see. like a firework. Don't ever go back. You might be escaping. You might be lucky.
It's confirmed. It's a boy thing.
It's a boy thing. Yeah, it looks like it, doesn't it? It does look like that. That's good. That's nice. Now we're going to test that, because if yours don't work again, then we can say that's definitely this experiment doesn't like boys. See, that might be the case. There we go. Off you go. Straight away. In, out. Let's see what happens. Is this a boy reaction? Very good. It's always good to put goggles on. Forgot to say that. Oh. Yours exploded all over the bench. Right, we're gonna get one boy experiment working. Loads of water. Loads of water. Loads of water. Did it explode before you put the lid on?
Yes.
Very good. Okay, there you go. Sit down. Okay, very simply, when you take ethanoic acid or vinegar, it reacts with sodium carbonate. And note, we have this special symbol. In chemistry, we like state symbols. It's really important. It kind of tells us how the actual chemicals, what their state of matter is. But if you see AQ, it means it's dissolved in water. And if you look at the second experiment, both of the state symbols are solids. And because they're both solids, the acid doesn't behave as an acid, therefore you don't get any chemical reaction, therefore it doesn't. Bit slippery up here now, Sarah. Therefore it doesn't actually go bang. But when I add that water, I will end up with aqueous here, and then I'll form carbon dioxide here. The carbon dioxide forces itself on that film canister, and the film canister will go bang. The nice thing about that experiment, you can do it at home. Very, very simply. Go into Boots. You can buy citric acid by the bucket load. You can go into Tesco's and you can buy sodium hydrogen carbonate or bicarbonate of soda. You can mix the two together, put it into a film canister, and do that all over your kitchen floor or your parents' lounge or wherever. Or what you do is you take that mix, add a whole load of icing sugar, swirl it all up, put that mixture into your mouth, and you've just made sherbet. Because that's all sherbet is. It's basically citric acid with bicarbonate of soda. As sherbet, there's no water, so the sherbet doesn't fizz. You put the sherbet into your mouth, and it starts to fizz, because in your mouth there's saliva. And the saliva acts effectively as that water bottle. And if you want to get out of your lessons, it's what I did when I was at school. I very quickly discovered that experiment. So what I would do, just before I was due to do games, I would put a load of sherbet in my mouth and then just close my mouth. And after a while, it would sort of go, bleh, and then I would go to the nurse and say, just been sick. And especially when it was raining, I would sit inside, watch my mates go out getting soaked on the rugby pitch, and I'd be in mate's room with a cup of tea and a nice chocolate biscuit, which is probably where I got my liking for chocolate biscuits, because most days that's what I did to get out of PE. But again, a good understanding of science can get you out of PE. How cool is that? So, this year my son was 18, and I thought, well, what can I do? What can I do to kind of make his 18th birthday cake that we forgot to make slightly more impressive than it was? And it was a TARDIS, wasn't it? Sorry, I forgot you did make it. Sorry, wife. I thought, what can I do to make it impressive? So I bought these. I bought these party candles, and I was so amazed at these party candles that I thought I would just love to bring these party candles to this evening. So what we'll do is we'll take that one off there. We'll take that off there. We'll unplug that. Put that over there. We'll stick one up here, because then you'll better see it at the back. We'll do the same up here, because then you'll better see it at the back. And we'll stick one in the middle. All the dangerous chemicals out the way. So, you may have seen these already, but I was just... Note the colour. You see it changing colour? Note it's red, it's now lilac. That was now that was sort of orangey yellow. That one's just gone yellow. This is now lilac. Now I have to admit, the one we bought, the one we put on my son's cake was about twice, perhaps 2 times, 3 times the size, which scared me witless when we set it off, because it really did go quite violently. But I thought to myself, I wonder what's happening in here. What's the chemistry? So. Oh, that's very good. Let's take you through the chemistry. So, it's all about combustion. It's all about combustion. There will be some organic molecule in these. Okay, possibly not as I've drawn wax, but some organic to get it to ignite. That requires lots of oxygen, produces lots of CO2. Can I just say, if you are someone who really is worried about global warming, apologies, I have just produced large amounts of CO2. We are producing large amounts of CO2 here. Okay, does mean that Milton Keynes will be by the coast. Bonus. Large amounts of oxygen is required, producing large amounts of CO2 and large amounts of water. That got you, in a sense, for it to ignite. All right. The key thing is, you didn't see it burn. All right. No one saw that candle burn. If you think you did see it burn, okay, then your eyes were deceiving you. All right. No one saw that candle burn. Okay. You saw a flame change colour, but that's kind of weird, because why did that happen? But what you didn't see is the organic burn. You couldn't have seen it burn, because the organic wax is colourless. Oxygen is most definitely colourless. Okay, if it wasn't colourless, there'd be a haze in this room, because 20% of this room is oxygen. Carbon dioxide is definitely colourless. We can all prove that. What I want you to do is, after 3, you're going to breathe out. And I just want you to breathe into your hands and just look at what you breathe out. Okay? So after 3, 1, 2, 3. Did anyone see a green gas? Okay? It was interesting. I did this for a year 5, and this lad said, yes, I did. And I then had to basically phone up the ambulance and say, okay, let's just get off to hospital. I'm sure you're very ill. But carbon dioxide is definitely colourless, and water is definitely colourless. So we couldn't have seen anything burn, because all of the products and all of the reactants are colourless. Okay? I'll explain what we did see in about 3 reactions' time, but just bear that in mind. You didn't see the thing burn. And you will never ever see anything burn. In fact, right at the end, I'll do a combustion where there is no flame. Right at the end, having explained to you what you saw. Now you also saw some sparks. Those sparks were due to iron filings. Iron filings, when they react with oxygen, make iron oxide, and the temperature of those sparks are about 1500 degrees centigrade. And I can sort of recreate that because here's a Bunsen. And what I can do is just sprinkle some iron filings. And what we get is a very similar process. It's quite a lot. Lots of the iron doesn't burn, so we can pick it up and we can basically do it again. Again, you can actually do this at home. I don't suggest you do, but you can pick up iron filings. But again, each of these are about 1500 degrees centigrade. Why sparklers are so darn dangerous. Okay, so why sparklers are so dangerous? Because when you see those sparklers, and you know they say do the handwriting because that's really cool. Every one of those sparkles that you see on a sparkler is the same as what you're seeing here. If you see those sort of flashes, those flashes are iron reacting with oxygen to form iron oxide at about 1500 degrees centigrade. So if I got those on my hand, it would be very dangerous. That's why everybody's at least, because I checked from the COSH, everyone's about 2 meters away from this. Okay? The nearest person is about 2 meters-ish away from this Bunsen for health and safety. That's the video. So, but it's really, really dangerous because, you know, it's incredibly hot. So that's okay. That's what we saw in that candle. Those sparks was because embedded in that candle was just some iron filings. So as the wax and the other chemicals that we'll talk about later on got down to the iron filings, so they heated the iron filings up, and effectively that reaction just took place. Great thing, combustion. Now, at this point I just want to stop doing some chemistry. Apologies for those of you who came here to see chemistry, because actually I'm also, bizarrely enough, in my spare time, part-time magician. And I've always wanted to do a trick in front of a live audience to see if I can make people go, wow. I have to admit, if you're over the age of 4, you might not go, wow. Unless, of course, you want to believe in magic. That would be cool. Okay, so we'll have young lady. Can I use you as a volunteer? Is that all right? Are you under the age of 25? Excellent. Hold those. Okay, so I've got a bag. It's a very simple bag. The key thing about the bag is empty. Do you agree the bag is empty? Yeah? Sure? Nothing in the bag. So what you're going to do is you're going to put those towels, silks, into the bag. Okay? Don't drop them on the floor. Just put them into the bag. Is that okay? Put them into the bag. So, in the bag, I've now got, I believe, 2 silks. Do we believe we've got 2 silks in the bag? Yes?
Yeah.
Okay, take them out of the bag. Just take them out of the bag. Did you put them in the bag? Are you sure? Okay, take them out of the bag. Asda, what were you doing? Because clearly, there they are. We'll do that again. Right, you put them in the bag. Right, Asda, all you need to do is take them out of the bag. It's very, very straightforward. You just have to take them out of the bag. That's all you have to do. Take them in and out of the bag. In and... Take them out of the bag. In and out of the bag. That's all you have to do. It's just take them... Now, you know, sometimes chemistry can appear kind of magic. Because that wasn't magic. You could do this trick. You could do this trick. Okay, see that knob there? Okay, we're going to press that knob there in a minute. But don't show the everyone else, okay? Okay, ready? We'll put them in. Okay, switch the knob when I was looking. Is the knob changed? Try and make it so no one knows. Okay, now ask this young man, this man here, to take them out of the bag. And here we go, for magic, here we go. All magic is any magic you see where someone puts something into a bag and pulls out, it's all because there's a little knob like that. Every single one. Every single, you probably all saw it. But every single one. The other magic trick, this is kind of bizarre magic trick, because I was thinking to myself, what can I do that's kind of, it says it's amazing. This is my book. This is my colouring book. This is kind of amazing. Okay, now, colouring books, okay, are quite nice because they have pictures in, okay? There's quite really nice little pictures. Well, they're really nice pictures. Until someone rubbed them out. Like that. Rub them out. Rub them out. See, when they rub out, the problem is, when you rub them out, the pictures lose their colour. That's a bit weird. Okay, then if you carry on rubbing them out, then after a while, you rub out and all of the pictures disappear. Now, you know, it's bizarre, because some people say to me, but that is obvious how that works. It's obvious. It's obvious how that works. So, there we go. Latin student, you can work out how it works. There you go, you can just work out how it works. When you've worked it out, tell everyone how it worked. Because it's all about... You won't get it because this is the book that I use. That was very good. The fact that you thought you had to turn it upside down, that was very good. We'll work out how we do that one later on as well. Anyway, back to chemistry. See, some chemistry appears like it's magic. Over here. So, let me see. Do I have 3 more volunteers? Yes, young man here. Yes, young man, have you not come forward yet? Yes, young lady, have you come forward yet? No, that's cool. There we go. 3 cups. There we go. Hold that wine glass. Hold that wine glass. I have one more. Yep, come forward. Yeah, young man in red, you come forward as well. Yes, you'll come forward as well. If you've not come forward already, that's fine. Oh, you have. Now, if someone hasn't come forward yet? Yeah, young man there, that's fine. For the rest, yeah, come forward. Yeah, young man in red, you come as well. Yeah, you come as well. Yeah, you can be the 4th, that's fine. You can have a wine glass. There you go, just stand in a row. Now, you are a magician, aren't you? Yeah? You are a magician, though you don't realise it. Because what you're going to do, what colour is this? It's see-through, it's got no colour, is it? Now, if you pour, let's put it in here. See, I'm not a magician, see look, I pour into a cup, and look, nothing happens. Okay, nothing happens. What I want you to do is to pour into their cups. Just pour the water into their cups. Just pour into their cups. And just pour into their cups. Just pour it, pour away. Pour away into their cups. Pour into their... Right, hold it up so people see. Pour into cup number 1. Cup number 2. Cup number 3. Now, were your cups empty? Guys, were your cups empty at the start when I gave my hand to you? Yes. They were empty, and yet you've just done a magic trick. See, I can't do it, look. I can't do it, because look. I can't do it. So you can do magic. There you go, put it back. Don't drink it, though. That would be not good. There were lots of water into wine tricks, but this one is not drinkable. Thank you very much, volunteers. Thank you. So, again, I once did that at an old people's home, just for a laugh, and it was amazing how some of these old people's homes, they kind of lit up as they thought, wow, free wine. So I have to admit, if that's what they were drinking, I did kind of worry. But again, what's the chemistry taking place? Well, it's very simple chemistry. Very simple chemistry. In that bottle, you wouldn't have seen it because you don't need a great deal. There's a chemical called phenolphthalein. Again, phenolphthalein is a really complicated structure. And when you have phenolphthalein and you have it in the presence of an alkali, then phenolphthalein turns, there we go, turns pink. So what I did earlier on, very simply, I got the cup, and this is the coolness of this experiment. This is all how much phenolphthalein you need. That's all you need. And then you just empty it out. I can even wipe this, and as long as there's a trace of phenolphthalein, the experiment will still work, because the phenolphthalein is now basically just a very thin layer at the bottom of this cup. So when I poured my water, which happened to be an alkali, I just changed the structure. And for those of you who know about acids and alkalis, you'll know the one on the right-hand side, left-hand side, that's right, sorry, dyspraxic. Right-hand side, this one has hydrogens on it, has hydrogen ions on it, therefore that's the acidic one. The one on the left-hand side, there isn't any hydrogen, the hydrogen ions have been removed, and that's what the alkalis do. They basically accept protons or hydrogen ions. And I could just change the colours and make it look a bit like magic. But it's not. But again, an understanding of chemistry enables you to do some wacky things. Oh, there's one more. Let's just set fire to that one while I'm walking over here. There we go. This is about 1500 degrees centigrade, as I said. That's very hot. In here, I have something that's very cold. And in here I have something that's very cold. So, liquid nitrogen and solid CO2 are what we call simple molecular structures. And what that basically means is that between any two particles in CO2 or nitrogen is a very, very weak force. And because it's a very weak force, it's very easy to basically do this. Okay, it's very easy just to remove them together. In the same way, there is a force between you and the chair. Okay, but if I say to you, everyone stand up. Okay, hopefully that wasn't that difficult. For some of you it was, I can see. Okay? Because there's a very weak force. And that's the kind of force between those particles in nitrogen or those particles in solid CO2. So they can be separated very, very easily. Now that means that for nitrogen, nitrogen is a liquid at minus 196 degrees centigrade. So that's about 200 degrees colder than what we would say was a reasonable summer's day in England. Whereas solid CO2, even more bizarre, because this stuff is a solid, there it is, whoops, but it sublimes. Now what that means is it goes from a solid to a gas. Now at primary school you're not taught about sublimation, okay? Partly because I think primary school teachers don't have to teach that. So they talk about boiling, they talk about condensing, they talk about evaporating, but they might not talk about sublimation. But this stuff is sublimed because it goes from a solid to a gas without ever melting. You don't ever get liquid CO2. Oops, sorry. There it is. Okay, I'm bouncing it around because it's at minus 7 degrees centigrade, and frostbite is something you don't really want at any age, I discovered. There we go. But it will turn into, if ever we leave it there, that will disappear, and you will never melt. You won't get a puddle of liquid forming there as you would if it was an ice block. It will just disappear. And because of that, you can do some really interesting experiments with solid CO2. First interesting experiment, cue very first loud bang possibly, is if you take solid CO2 and you put it into a balloon. Cammy, can you remember how much I put in last time? How many bits? 7 or 8. Right, 2, 3, 4. How much? 10. 1, 2, 3. Get in, go on. 3. Can't get that bit in. That's quite a thin bit. 4. 4.5. 5.5. Oh, that's quite a big bit. Ow, that's going cold. Yeah, get any more in there. Okay, so I've got solid CO2 in the balloon. H 9. No. So I've got solid CO2 in the balloon. There we go. 10. Get in. That's one more. 10. That bit. Solid CO2 in the balloon, and it's going to start to sublime. So it's going to start. One more for luck. It's going to start to sublime. So it's going to start going from a solid to a gas directly. So if I tie up this balloon and we warm it up a bit, the balloon is going to start to just get bigger. Okay, this is just self-inflating. There we go. What we'll do is we'll put it in the sink with some hot water running over it. And I have no idea when that's going to go bang. So apologies if you like don't like loud bangs, but at some point that will explode. Just to show you, it is getting bigger. That's how big it is now. Okay, so it is getting bigger, and it might go bang at some point. So, that's solid CO2, but you can do more wacky things with solid CO2, because the nice thing about CO2 is that when it sublimes, I can make some quite interesting bubbles.
Oh, it disappears when it hits the floor.
Now, you'll note these bubbles are cloudy. Whoops. You'll note these bubbles are cloudy. Of course, these bubbles are cloudy because what we've got here is clouds. Okay, all clouds is, of course, is condensed water vapour, and that's basically what we've got here. We've got water here at minus 77 degrees centigrade. The air at minus 77 degrees centigrade is basically passing along the rubber tubing, condensing any water that's present in that tube, and hence forming a cloudy bubble. That's on a small scale. So again, It's always good to experiment, isn't it? So I got thinking, and I thought, well, perhaps what might happen if I could do it on a big scale. Yeah, the balloon's still reasonably sized. So, what I'm going to do, I've got water in here. I'm going to see, I'm not brilliant at doing this, so I might need a volunteer to see if they can do this. It'll probably have to be an adult because you need a really steady hand. What I'm going to try to do is see if I can get a film on the top of this bin. So when I put CO2 in here, the CO2 will push the film up and hopefully we'll get a beautiful bubble appearing on top of because once you've failed once, it's very difficult to succeed the second time. I'll go the other way. Go on, 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 go on. You've ever seen any movie like Harry Potter or any movie like Wizards versus Aliens or any other movie where you have, or TV program where you have any kind of potion bubbling away? This is all it is. Okay, they've just basically got a job load of solid CO2, commonly called dry ice, and they just add it to water. And when they add it to water, you make clouds. Can I? Oh, where they go? Can I get it to? Am I going to get one more? I don't think so. Oh, am I? Does anyone want to have a go? Has anyone got a really steady hand? Is there an adult who's got a steady hand? It'd be good if it was an adult, because it's just that. Any adult got a steady? Mr. Jenkins, have you got a steady hand? If you do it, then that's, you'd be making me look stupid, that's fine. Let's see if we can get one. But again, if you note, can you see the water vapour is basically falling that way? It's falling downwards. That's because CO2 is heavier than air, so it's basically coming out of this bin and basically descending straight down to the ground. Here we go, give a big show if this works. I suppose you've got more patience than me. You're slower, probably. Come on, David, you can do this. That's first time. That's typical. That's why he's replacing me.
No, that's just good luck on my behalf.
Go on, go on, go on, go on, go on, go on. Go on, big cheers. Big cheers. Big cheers. Yeah, no, obviously doesn't like me. Can you see the sort of the coloured bands? Okay, that's where light's being diffracted off the surface. Interesting enough, when this bubble film bursts, what you will find just doesn't like me. What we would have found, and I got blown on it, is that those colour films would suddenly have disappeared, because the point when your bubble film is one molecule layer thick, it no longer diffracts light off the surface, it absorbs light, and say the bubble suddenly goes black. It's really bizarre. Again, you can play around with this at home. You can pinch some solid CO2 off Buckingham University, who gave me this. That's solid CO2. The balloon is now that size. It will go down at some point. So that's solid CO2. What I've got in here is something that's a lot colder. As I said, it's at minus 196 degrees centigrade. This is liquid nitrogen. And liquid nitrogen has some very strange properties because everything that I put into here will be boiling hot compared to the liquid nitrogen. Alright, so if I put something in there that's at 20 degrees centigrade, i.e. roughly the temperature of this room, it will be 200 degrees hotter than the liquid nitrogen. The liquid nitrogen will instantly boil. The liquid nitrogen, if I put a piece of rubber tubing in, will then basically pass up the rubber tubing. Because we're at minus 196 degrees centigrade, water vapour will condense. But not only will water vapour condense, it will then freeze because it drops below 0 degrees centigrade, so coming out of here will be hailstones. But not only will the air, or the water vapour in the air, suddenly condense and then freeze, oxygen that's present in the air will also liquefy. So coming out of here in a minute will look like a waterfall, and that also a fountain spray, and that fountain spray will contain solid bits of ice and liquid oxygen. And it kind of looks like this. Now, after a while you'll see it stops. Slowing down, it's slowing down, it's slowing down. And of course it's slowing down because the air down, the rubber tubing down there is now at minus 196 degrees centigrade. And rubber at room temperature does this. Okay, we're used to rubber bending. I can bend rubber, I'm very strong. This has to be a sick former, so James, you can volunteer. But you'll need gloves, because I don't want you getting frostbite, your mum would never forgive me.
You're right.
There you go. So you're going to take this off and just try and bend the rubber, okay, at that end. Alright? And then you can just explode it. There we go. Now, just to show that this isn't fake, this wasn't a fake bit of rubber. Okay, let's warm it up. Okay, just to show this wasn't fake. Just warm it up. And now, okay, it's just at minus 196 degrees centigrade. Basically, the molecules of rubber basically can no longer flex. Because they can no longer flex, you basically have a solid bit of rubber with all of the added effects. Thanks, James. The other thing can happen, and this is kind of dangerous because I don't know where this is going to fly to. So if you're at the front row, kind of block your eyes. Because what can happen is it actually shatters like glass. Alright, and we don't expect rubber to do that. Because we expect rubber to kind of be all floppy, because in rubber, the molecules can basically bend. Because the molecules can bend, rubber can bend. But when we freeze them in place, we basically can't bend them. And I have to admit, I showed this, when I did this at year 5, I always make sure that if there's a male member of staff there, I get them up the front, and then they go butch and they kind of just snap. Can I say, if anyone's pacemaker's now going, apologies. But actually, if James had carried on flexing, actually what would have happened is it ultimately just snapped the rubber in half. Because again, it no longer bends, it just shatters. The other thing you can do with liquid nitrogen, again, you can do some magic. Or you can do something that looks like magic. And we can self-inflate a balloon. Not because anything's in it. So what we can do is we can take out the balloon and we can throw it on the floor, and we can take out a balloon. And it's basically self-inflates. If I get the other one, I'll see what the other one is. There we go, put the other one there. That's kind of bizarre, because if you think what you've just seen the balloon pop. Okay, now if the balloon popped, there was no way a balloon that's going to pop is going to fit into that hole. This balloon here, note, doesn't fit into that liquid nitrogen duo. Okay? Doesn't fit. I pulled it out and it's self-inflated. Now, I once watched a magician do that. Pulled it out, got something like this, pulled out this balloon self-inflated. Everyone went, woo! He went mind control. I said, put your hand into that same package, just leave it there for 10 minutes, and then smack your hand onto the bench. That would be funny, because of course, for those of you who are squeamish, you might want to block your ears. What would happen? You'd have the same expression as that bit of rubber tubing. It would split, but because all your blood vessels have frozen, your fingers would fall off, but no blood would flow until about 10 minutes later, when your blood is then defrosted. And then suddenly you have like special powers of blood firing out of these gaps in your hands. Again, not something you want to try at home. So, again, how did I do that? Well, very simply, earlier on, what I did is I took a balloon, I blew it up a little bit, I put the balloon into the liquid nitrogen. Of course, the air starts to condense because the water vapour turns to ice, the oxygen turns to liquids, so liquids take up less space than gases, so the balloon therefore starts to get smaller. Let it get a bit smaller. I blow it up again, put it in again, put a bit more air in, gets slightly harder because the thing doesn't want the air doesn't want to actually go in because of the pressure of this balloon. But anyway, put a bit more in. Put a bit more in. Seal it up. Ooh, try and seal it. Oh, not seal it up, as the case might be. Oh, no, we'll not seal it up. Oh, no, down. Hold. A bit more in, that'll do. Okay, now seal it up. Now put it in. Let it condense. Let all the liquid oxygen condense. And then when I take it out, the balloon warms up. Get a beautifully self-inflating balloon. But of course, look, no longer fits in here. No longer fits in here because gases take up more volume than liquids. So when I was condensing it, I could force more air into that balloon. The gas turned into a liquid. The balloon got smaller. I could force more in until ultimately you get a balloon that doesn't fit. And I've seen this with someone who's got more puff than me. Pulled it out and the balloon was kind of this kind of size. And it was really impressive. Now, we've got to get rid of the liquid nitrogen. So you might want to lift your bag slightly off the floor. Not that it will actually do anything to your bag, but the liquid nitrogen is basically going to move that way. It can't go, of course, here because of obviously electronics. You might get a bit cross with me. So it's going to kind of, we'll throw it that way perhaps. Perhaps we've got any more. We'll throw it that way. So there you go, liquid nitrogen. Okay, so, I've got to longer than I thought I was going to be. Is everyone okay? So I've gone on slightly a bit longer than I thought it was going to. Is everyone quite happy to stay? Okay, cool. I've got two more quiet experiments, and then basically we'll need to have a bit of about a 5-minute pause just while we set up the final 5, because the final 5 are slightly loud and slightly more dangerous, and we just need to have slightly more protection up here. So we'll do 2 more, and then we'll go for a slightly loud experiment. And for this experiment, I need 3 volunteers. So we'll go young lady, yes, young lady from Buckingham Primary. Yes, young lady here, yes, we do. Okay, we've got one more, we've got some more experiments coming for volunteers, that's fine, yes, so there you go, you'd like, hold that one and that one. Hold that one and that one. Okay, and then your one is all the way down here. This is your one. If you want to go in the middle, so if you come here, so then, so now, this used to be, when I first arrived at the Latin 17 years ago, I didn't really understand, I suppose, how seriously parents took the open evening, sort of year 6, 11 plus open evening. I didn't really see that, so I did this experiment. And what I said to the parents is that this is actually much more important than your 11 plus. Much more important than your 11 plus. This is what's going to get your child into the Latin, because this experiment is mind controlled. And either your child is able to think blue and control an experiment, make it go blue, or they can't. Now again, I have to admit, I didn't realise that parents would take me seriously. But in the second year of doing that, I discovered that one parent, as she was screaming at her child about going blue, going blue, going blue. And I had to point out to her, because she was screaming, she was obviously affecting her child, so stop screaming. And as the child, mum has stopped screaming, so the thing went blue. I said, there you go, just don't scream at your child ever again. Non-constructive. But I was told I wasn't allowed to do that experiment anymore. So this is a mind-controlled experiment. This is what I set up. So you can imagine, picture it, you're 11 plus, open evening. You want your children, you're thinking, I want my child to get to the Latin, goodness, they've got to do this 11 plus thing, and I've just been told by the head of chemistry at the Latin that this is what's going to get my child in. So what you're going to do is you're going to mix, okay, the little one into the big one. Okay, the little one into the big one, the little one into the big one. You're just going to think sort of blue, though it might go brown. They were going brown earlier, I'm not sure if we had any in this starch. So that's what you need to do. So all at the same time, otherwise it's not fair. So hold them this way, hold them so everyone can see it. Okay, little one into the big one. Don't pull the big one into the little one, otherwise it will go all over the floor. So that after 3, so we count them down. Ready?
1, 2, 3.
In. Think change of colour. Think change of colour. Think change of colour. Think change of colour. Think change. Now you can imagine the parents now. How anxious would you feel that nothing is. Oh look, 2 have gone and 3 have gone. Okay. They all do 5 There you go. Thank you. So again, why didn't they go blue black right at the start? Well, of course. Okay, leave it there. Brilliant, thank you. Yeah, do take your seats. Thank you very much. Why didn't they go blue-black at the start? Well, they didn't go blue-black at the start because I was kind of cheating. Okay, I was kind of cheating because there were, in that experiment, 2 reactions going on, and I put the wrong PowerPoint slide up, but hey, it doesn't matter. First wrong one in the evening. There are 2 competing reactions. Competing reaction number 1 makes iodine. And iodine, basically, because we've also in there got some potassium iodide, I-, makes this thing called the I3- ion. And when that ion reacts with starch, you get this beautiful looking complex where the starch molecules surround those I3 minus ions, and the colour of that complex is this sort of black-blue solution. So that's experiment number 1. But in experiment number 2, that was going on in that flask at the same time, I had this chemical called sodium thiosulfate, and sodium thiosulfate reacts with iodine and destroys the iodine. Gets rid of it. And if there isn't any iodine present, that first reaction can't take place. And if that first reaction can't take place because there is no I2, then I won't get a blue-black colour. So depending how much sodium thiosulfate I put into each of these, I can control exactly when they go. Now, had I been slightly more professional, what I would have done is I would have timed these exactly so I could have gone, yours is going now yours, and unfortunately yours is never going to go until now, and then it would have gone. But as I said, I didn't want people holding something that isn't happening up front because that's just kind of cruel. Also, I was told by the then head teacher many years ago. So I got to thinking about this experiment. This is called a clock reaction. It will change colour at a specific time, depending just how much of this I've got present. And I got to thinking that, well, I could use that experiment to do even more magic. Even more magic. So again, I need 3. Yep. Yep. And yep. Now, next experiment, you'll come up the front, okay? Yeah, 3 young men. Come up. Forward you come. Forward you come. Okay. Do you like mess? Are you into mess? Yeah? Good. That's good. So put some of that in there. Put some of that in there. Put some of that in there. How do you care if your hands change colour? You do. Do I have another volunteer? You do. No, you do. It might not change colour. It just might. Okay, so there you go. So what I want you to do is to take this lovely bit of cloth, and you can make it as mucky as you like by dumping it into that iodine. Make it as mucky as you like. As mucky as you like. Really get it in there. Really get it. Come to the front so everyone can see. Get it in there, get it in there, get it in there. Get it really, really as mucky as you like. As mucky as you like. Make it really, 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 really. Okay, not that mucky. That's a bit thinner. And that's just disgusting. That's worse than yours. Yours is worse. Yeah, you put it all over your fingers. That's okay, we're going to clean your fingers in a minute. Okay, so, when you have mucky things, you wash them, don't you? Yeah, that's good. Okay. Wait a minute, because there's loads of you, so you've made them really quite messy. Let me just, so this is water softener. That's why it's slightly cloudy. There we go. Right. Just wash it. Pour some of the water into there. Okay, just wash it. Make it nice and clean. You can take it into it. Pour the water in there. Make it nice and clean. Make it nice and clean. You're washing things. Very important that you wash things. Make it nice, really nice and clean. That's it. Now go to the next person. Just nice. Wash it nice and clean. Just wash it. Wash. Hopefully they're getting nice and clean now. Because I said to Sarah I'd give them back to her clean. So this is her handkerchief. Have you got it nice and clean now, boys? So you've made them worse. Show everyone that way how can I say, don't ever get them doing any washing in your house. Look at this. This is just like this is horrid. This is horrid. Young man. You look like the kind of person who's clean and tidy. Is that you? Okay. Well, you're going to see. Basically, they're going to hand you each of your cloths. Okay, you're just going to wash it in my magic water. Okay, so just take it off them, wash it into the magic water. Just wash it, just dump it in. Okay. One more. You might have to clean it now. You might have to get it nice and clean with your fingers, just so it's nice and clean. There you go. Does that look nice and clean? Now hand it back and put it into your dirty water. Take the next one. Wash it nice and clean. Put it into your dirty water. Just keep it washing into that dirty. Put it into the dirty water again. Take it out again so you're in your dirty. Okay, take it to the next again. Pass it back to the boat. That's a nice clean cloth. Put it to your dirty water. No, your dirty water's no longer dirty. Okay. Take it to the next, to the last person. Get your cloth, put it in, just wash it. You obviously do this. You obviously, definitely, person who should do some washing. Definitely, go home and start washing. You know, in terms of clothes, in terms of like, you know, when you're having lunch, wash that cloth off on the plates. Put the dishwasher. Okay. Is your water clean? Okay. Last one. Let's make sure it works for everybody. So what on earth? Let's see if this works. Keep. There we go. Thank you very much. So those of you who are thinking science, okay, those of you who are thinking science are already thinking, well, we know how that works. That's experiment's obvious. Because this grimy water that made the iodine go blue-black, that must be starch. That must be starch. Because when I have iodine and starch, I get that beautiful, well, the colour's horrible, but the actual picture is beautiful, of the starch complex. And this must be that thiosulfur, that S2O3 2- ion. Because this stuff just destroys iodine. When I get it back, will I have enough to get it back? Will I? Almost run out of chemical. That must be sodium thiosulfate, because when I take sodium thiosulfate and I put it to iodine, the iodine is destroyed, and therefore the blue-black colour disappears. And that's all I had. Not magic, very simple chemistry. It's a clock reaction, so therefore it made that iodine again, as all the thiosulfate was destroyed. Okay. So we need to have about 5 minutes. Is that okay? And then it'll be about 10 minutes after that. Is that okay with everyone? Okay. So if you need a loo, now would be a good time to head to the loo if you need to go. That's all right. Keep that going. Keep that going.